Ladies and gentlemen, please welcome our next speaker, Nelson Vides, presenting the topic, a murder of crows, actors, instrumentation, and load testing as part of the TDD cycle.
Hello? Yes. Alright, I cannot resist this. It's pronounced Vides. It comes from wine, so I'm proud of it. Anyway. That's a quote from Macbeth. It will have some meaning later. Are you all familiar, more or less, with Macbeth? Like a guy wants to get some power. He betrays his family, kills his brother, if I remember correctly. His wife is behind him, telling him all the time what to do and how to get more power. And it gets like very like telenovela, but Shakespeare. Anyway, murder of crows, actors, instrumentations, and load testing as part of the TDD cycle. I work in Erlang Solutions, a company that specializes in scalable, fault-tolerant, and distributed systems. With all the keywords you can imagine, fancy projects, very interesting clients. We specialize mostly in two languages, Erlang and Elixir. You all use these languages even if you don't know. For example, WhatsApp is 100% Erlang in the backend. Discord is all Elixir, the backend, two classics, plenty of others. This is my GitHub if you want to find me somewhere. And my two main babies, a messaging server and a load testing tool that we are going to get to. And you can find me by that picture everywhere in social media except LinkedIn, because I was told that I have to look professional in LinkedIn, so in LinkedIn I have something cool, but otherwise that's me. My career, you could say, that started more or less this day. I was a programmer before this, but like this is the important day, and there was a photographer that day, so I'm very fortunate to have this picture. I was at this point junior mid developer in C in telecommunications, and I was frustrated with one specific problem. We had a software that was to be deployed in servers. My company was responsible for the whole stack, including the hardware. So we were selling the hardware with the software installed. Everything was like one unified box. And we had this challenge that software would get slower if you put it on a bigger machine, which was very counterintuitive. The thing is that now bigger machine doesn't mean a faster core, it means more cores. And you started reaching log contentions. So for some time, I was trying to deal with this in C until I met this guy and I discovered that he already did what I was trying to do, but like with my incredible lack of experience. He's one of the creators of Erlang. I met him this day by accident. I didn't know he was there. Somebody told me, hey, we can use Robert Birding, and my head was like, wait, what? Then I moved to Erlang. That's where I code now. Through him, I met my company. Let's get to some topics on load. That's a good old statistic from Google. It's from 17, yes, 17. Bounce is the probability that somebody that enters your website would abandon the website. It increases dramatically the slower your website is, and Google still today uses this to penalize your website. If it's slow, it's gonna just put it further down, because Google wants to, you know, the users of Google want the fast experience. So if your website is slow, people are gonna blame Google. So, you know, that's how they make money. Almost 20 years ago, Amazon found that every 100 milliseconds of latency would cost them 1% in sales. In context, please check the source, somewhere there. By today, that would be a few $billion a year for Amazon. In general, imagine 1% of your revenue, whatever your business is doing, imagine that you would just lose 1% of it. Can hurt a lot. I mean, maybe it's not bankruptcy, but it can make a big difference. A broker for trading could lose $4 million in revenue per millisecond. So that builds up very fast if their platform is 5 milliseconds behind the competition, because it's bidding, so it's who makes the faster bet. An example, a very innocent example from the mailing list. This is from January. this has been making my merge window miserable. By, like he says, you have been warned. This is very polite by today's standards. By Linus Torvalds, January 2024. Something was making the build very slow. He went from 22 seconds to 44. Drove him mad. He found the pull request that in the merge that introduced this slowdown, and he said something in your merge is going to be reverted. Saturday 13, just a couple of days later, he says that we have lost power and internet thanks to a winter storm, and then he goes to make fun of what people in Oregon call winter. He's from Finland. So that's just 3 days later. The merge window is paused. The next day, this little tiny fix is released. It was just like just calculating some margin, like it was a no-brainer. But Linus was out of connection, so this took a few days to be taken care of. What if this happened? This was only for the compilation, but what if something like this happens to a database? For example, we all use databases under the hood. If it happens to a video game engine, you know, frames per second, and you get to buy so much expensive hardware to play this game, and then the game is slower, not that good for your business. So let's talk about performance. Ready? I still don't know how fast I'm going to go through this. You only care if you have a merge kit. End of the talk. That's the most important point. If you can ignore me from now, please don't. But this premature optimization is the root of all evil. We have all heard this quote, I hope, by the one and only Donald Knuth, the father of algorithms. This quote has some context. We should forget about these things 97% of the time. It's the root of all evil. Yet, it's that critical 3%, and why not? It's very tempting. I'm obsessed with performance. I tend to overlook for this 3%, and I'm blamed for it often. So I'm also reminded of the whole thing often. So, focus. Benchmarks. You only care about code you have benchmarked, right? Don't forget that. Most important point. I had, this is playing well? Yes, fantastic, good internet. I had a very nice physics teacher in high school. And we were studying at some point fluid mechanics. And he gave us this example. I'll never forget it. It was impressive. That's a bridge in the Tacoma Narrows, north west of the US. During construction, it was behaving weirdly, but just a couple of days after construction, this happened. The bridge was evacuated. There was no human casualties, only one dog inside of that car. That was the only casualty of the whole thing. This, if you look it up in Wikipedia, like it's not a crazy thing. The wind was something like 25 miles per hour. Don't ask me in kilometers. I'm a great supporter of the international system, but Wikipedia had it in miles. I don't know, what is it, like 40 kilometers per hour maybe? It's not a lot. So the question is, what the hell happened? Like, it's not like crazy force. No, don't play it again. Sorry, the arrow things that I want to play again. Now, yeah. We went one day from this kind of bridges, from, you know, the Roman Empire, big, solid pieces of stone that you could just hammer down and nothing happens. And one day we went to these kind of bridges that are way bigger, but actually weight a lot less. And they are flexible, they are hanging, then they become susceptible to new forces. Like, for example, we used to go from these kind of computers that I could punch with all my anger and I would probably just break my hand. And we went to this world, or to this laptop that I have, that if I punch it, presentation is over. There are new forces that make a difference now that I didn't used to make. Those computers were used by like 3 guys in the lab that just knew how to use it and they took turns. And this is used by everyone. You never know in which ways. You all heard, like, God knows what your client is going to do with your software. So we went from a bridge that it was like indestructible because like it was just one big solid thing, but now gravity is pulling everything to like 3 points of concentration. Similar analogy, we went to a single massive computer used by 3 people to very strange cloud deployments used by sky's the limit. So these things, we need to test them. And we had one very important luck. I'm going to talk about computers, not about bridges. That was my last analogy. I'm not a bridge engineer, but we have one amazing advantage that architects or bridge engineers don't have. We can make copies of our program and see what happens, and just break it. Just do whatever ugly stuff. You cannot build 2 bridges and break one to see. No chance. But we have that luck. It's virtually free, of course, consumes hardware, but you get the idea. So we need to test things. I'm going to give a few examples based on this little baby of mine. I mentioned it before. It's not mine, it's my team, but I'm very proud of it. It's very close to my heart. It's a messaging server written in Erlang, extensible, scalable. I mostly like to emphasize the extensibility. We can customize it. So some examples are going to build on it. You can have a look. Robot, scalable, extensible, instant messaging server. IM comes from instant messaging. And we are going to run a little performance testing. One of the things that this does, addresses in this chat application, it uses the XMPP protocol. So it works, the address is something like an email, but you just get that extra resource. That's how you distinguish more than one device connected to an account. And that's how you can federate servers when you send a message from, when you send an email from Gmail to your friend that has an account in Yahoo. They just send a message to each other, you federate the servers. So a very common operations is to parse this thing and turn it into a data structure, operate on your data structure, and vice versa. The parsing needs internationalization, like your URLs, to defend against Unicode that makes it look similar, so it has some string. And I use this library called Benchy to test the old implementation that we had, written using an if. That means natively implemented function. Erlang is an interpreted language, so sometimes for performance reasons you want to implement something in C because it's like it's perfect, so you do it very fast. And that was our old implementation. And then we wrote a little one in pure Erlang code, randomly generate like 3 UUIDs. Let's say that that's the username, the server, and the resource, and let's see how parsing happens to them. And turns out my pure C code was 2 times slower, and a tiny little bit more memory use, like 40 bytes, doesn't matter, but 2 times lower. So this is a very single algorithm. Like you saw how complicated it can be. Like you just need to find the @ the slash. That's crazy, but hey, pure code was faster, easier to maintain, get rid of the C code. So benchmarked. Another example. Bit more complicated. The protocol works on XML, is the markup language. So that's another operation that is very hot code. You do it for every single message that you route everywhere. You need super fast XML encoding and decoding. So you try it in C, then try it in pure Erlang, make a comparison with like different sizes. I just make here a few different inputs. This time, systematically for all of them, the C code was way, way, way faster, and also consuming a lot less memory. But on average, you see somewhere between 20, 30 times faster. There is this one that makes a big difference. All the others were between 20 to 30 times lower on the pure Erlang code. This one is only 5 times lower. What happened here in this size? I run this on this machine that I'm showing you, and then I'm doing this presentation. You get the specs. That's cache size. So at exactly 5 kilobytes, the word didn't fit in cache and there was some memory, so you get a curve. But then when you get something very big, cache doesn't make a difference anymore compared to the whole encoding and decoding. So that's very good to know. Like this slumps in my performance because I can optimize for what will be my usual packet size. How big are your messages? Do you send to your grandma messages that big, 5,000 characters? It's usually hello, how are you? And I can optimize a bit. This was wrong with Benchy, a little framework that gives you a lot of nice statistics. It's written in Elixir. I know the developer and he's lovely, full open source. you can also have a look here. You saw generally the very intuitive. You give it some inputs, a bunch of functions. You can also calculate memory time running in parallel, etc., etc. And now a little bit of load test. I checked a few linear algorithms. Now let's see what happens when I want to connect users. And I'm gonna use this little library. I get the specs for 2 users, so randomly create a username, password, whatever, connect them both, and have them both do this thing. Create a stanza, send it. Stanza is a message in terminology, and the other user waits for the stanza and verifies that it is correct. And you just do it, for Alice to Bob and Bob to Alice. So you check, you load test this kind of scenario. Also, this runs in a loop 60 times, and you wait 10 seconds. So Alice and Bob send a message to each other, wait 10 seconds, do it again. It runs in this infrastructure. Load testing master node and 2 worker nodes, 2 MongoCIM nodes using Postgres. All of this is also archived. 100,000 users, 1 every 5 milliseconds, and as I said, every 10 seconds send 60 message in total. And these are some results for a comparison. I wanted to compare a pull request to master with some important changes. So we wanted to make sure that at the very least doesn't get worse. So here we get how it was before with a new underground under the hood library, Nisha CTS. No need to bore you out with the details. Same stuff, a little bit. The medium and the 95s is a little bit better, but maybe it doesn't make a big difference when it comes to the user experience. If the message took 3 or 4 milliseconds to arrive, the user doesn't notice that. His phone, the internet is probably slower. Anyway, so I'm good to go. My new code is not making my whole system worse. This was used by my other little baby that I introduced at the beginning, Amok, that spawns all these users and connects them all and runs the test as I want to do it. And there is one last kind of test, stress test. For this one, I'm not going to give you any fancy example because it's very hard to give one. What I want to do in a stress test is to kill it. I don't want to see how it works when I connect 100,000 users. I want to see how it dies. That's what you cannot do with a breach. You can just make copies. I will share with you insight on how to do it, but I will skip an example because they can be very convoluted to generate. So we get 3 kinds of load tests. Really load is the one in the middle. You want to see how it behaves at high load, but you get the usual micro benchmarking. So performance at minimum load, you are loading one thing. And the stress, you see how it dies. That's the 3 performance tests that you should probably run. There is a lot of others. One that is also a very good idea is a long-term test. Some things, when you have a memory leak, you only see it when it has been running in production after a month. So run a load test and keep it running in the background for a month to see if it degrades. This is more complicated, but these 3 are relatively low-hanging fruits that you should be aware of them and start doing. So we know our test. Now we need to know the purpose. Test-driven development. Everybody knows this, right? I don't need to argue. I don't need to try to convince you. I hope it's clear. You know how it works. You write a test. For example, this is Erlang code, by the way. Name of my test, I'm going to run a story. Scalus is a helper library for the XMPP clients. I will give it to users, and I will tell it to create 2 users, completely fresh. So there is no, I can run them in parallel, and execute the story. The story, let's go through it. Just like in the load test before, create a message, have Ali sends that message to Bob. Bob waits for the message and verifies that it's correct, and vice versa. So my usual functional test, I can send the message, and as I say, you wrap it into a story. Scalus automatically generates the clients and does the whole thing. Cool. Fails because TDD. Now I have to make it pass. Not going to show you the source code. Cool. Green. It's, okay. You also, of course, get the inits and, for initialization. Excellent. Refactor, make sure the code is great. Repeat, next functionality. You get the idea. You probably already knew the idea, and I only repeated what you already knew. Now, very important. This is how long my test took. 0.75 seconds. That's how long it took to create 2 completely fresh users, connect them, have them send the message, disconnect them, and say the test is green. Really, what I want to test is that I can send the message in a different place. I already tested that they can be connected. But this is how long it took the whole thing. So let's benchmark it with the previous tool. This time I only want to know how fast is the message delivery. I don't want to, this previous time was taking into account connecting the user and so on. This time I'm going to consider that they are already connected. So before each scenario, I'm going to generate 2 connected clients, and after each scenario, I'm going to disconnect it. So these 2 operations are not part of my scenario. And in the scenario, I'm going to do exactly the same that in the previous 2 examples: send 2 messages, receive them, verify, etc. This, as I said before, you generate them, the message, generate the message, verify when you receive them. When it's done, disconnect the users, and then repeat. In my computer, this one again, in the Mac, Mongoose IM this time is running on a separate box, but it's running on the same network. It's a Linux with these specs, and the scenario is being run on this MacBook that I'm presenting with, so you get the specs same than before. On average, my average is 600 nanoseconds. I'm very happy about this. This is the amount of operations per second that I can do. Here you have some statistic. The worst case, you get the 155 milliseconds. But here I'm running 1 test at a time. There is no parallelism. In a real server, I sell you a messaging server, and you are gonna get Christmas and everybody writes like crazy. What happens that day? So I'm gonna try to run it in parallel, because Benchy also gives me tools for this. All the same logic than before, but this time I'm gonna run the test first of all for longer, not the default 5 seconds, but let's see, about 30. And the parallel is a flag that I'm going to tweak. I'm gonna get these results. The parallel is use 1, you know it before. Parallel is 12. Both of my computers, both this one and the other Linux box, has 12 cores. So that's more or less where I would expect that things starts getting interesting. At there I get the average is 1 millisecond, worst case is 7 milliseconds, still is fantastic. But then I see that when I grow, I just try up to 64, the grow is much less than linear when here is quadratic. So I'm very happy about my server. I have benchmarked, and I have a baseline for future changes. Now, define the specification. I want to sell you a server that delivers message, but that delivers them relatively immediately. This is the first point I want to make. The relatively immediately is part of the specification of the product that I want to sell you. And that is very important. So I need to define the SLAs, latency versus throughput, and expected behavior. SLAs, if I want the, for the statistics, not every message is going to be the same. So some people tell you the 200 milliseconds message delivery. 200 milliseconds what? The median, the 99s, the maximum. To define these things. You define your expected worst case, and the really, really bad, this should never be tolerated. So that's your maximum. Same for HTTP, first content delivery. That's where Google is going to penalize your website. Latency versus throughput. And also, when it dies, I want it to die by full death or partial death. This comes from the electric grid terminology, when they disconnect part of the grid but not part of the other. Or if I want to do a brownout, which is like lower the voltage. That is, I'm going to take longer to deliver the message. I'm going to lower the quality of the service. This is important because for the electric grid, you cannot do a brownout or any kind of blackout to a hospital, for example. That, it's better to disconnect some neighborhood and keep the hospital fully connected. So it depends on your use case. You need to define these things and have them tested. Now, this is the baseline, the previous test that I have in this machine. But what if I run this test in another machine? I was showing you wall clock times, but this has limitations. The first funniest one that usually it never happens until it does, but really it's such an edge case. It's just important to know the time warps, time corrections. because, I don't know, a fluctuation in the sun and the Earth took a nanosecond less to rotate, and there are atomic clocks that can detect that everything is corrected real time. Your computer eventually gets the correction. Hey, get your clock 0.76 nanoseconds behind. Your computer does this, jumping in time. So your measurements of time can suffer this. It's really rare, but it's important. Also, they are expensive and they make a lot of noise. This leap forwards or backward in time. Expensive because it's a global variable. In a computer with 64 cores, it's a unique thing. You need memory barriers to access. And it makes a lot of noise. This is affected by voltage, just to name one thing. So alternatives, performance counters. Do I need to introduce perf? Anybody doing some kind of low level, or sometimes not even low level, but like concerned with performance, you should be familiar with this tool for measuring things. Perf is really a front end to kernel counters. Database counters. You want to test how long the database took to make an operation. If you put it on a different hardware, it's going to take a different amount of time. You want to know if your query is correct, you check the database counters. All databases, Postgres for example, offer you this kind of things. And interpreted counters for interpreted languages. Java is one example. Not familiar with all the languages in the world. Of course, Erlang has ones. It has their own. The tests that I show you time because you are not familiar with Erlang. But Erlang has a concept of unit of work, is what I actually use when I want to test if my algorithm is correct. And I know that the units of work will get worse or better as I change things, and how long this takes is really hardware dependent. But I have a reliable, noise-free counter. Deal with noise. What kind of noise depends on what are we measuring. You're all familiar with throughput, latency, and memory. Throughput and latency is usually a trade-off. You cannot have both. You can optimize a lot of both, but they tend to fight each other. And you will say that for your test, you want a static threshold. For example, I want my test, the message delivery to be 5 milliseconds, the pure message delivery. The static threshold has some disadvantages. It's manual work. For every single test, I have to decide. And how many tests are there? There is no context. There can be, for example, if my threshold was 5 milliseconds, I'm running currently on 3 and make some pull request that goes to 4.9, it's still green. But the next pull request only changes the readme, and because there is noise, the readme change is red. There's no context. And background variance, noise. So I need automatically applied thresholds that I don't need to manually decide, that are aware of the context, and that they are resilient against variance. So we are going to use a little bit of statistics. What is variance? The red thing has a very little variance. That means you have your average, but all the population are close to the average. So that is little variety. And the blue one has the exact same average, but a lot of variety, so variance. And the square root of variance is called the standard deviation. And there is this rule, the 68, 95, 99, that says that all the population of a normal distribution are going to be this far away from the standard deviation. So when you get your average, 68% is going to be one standard deviation around the average. And 99.7%, that's pretty much the entire population, is going to be 3 standard deviations away. So, okay. Track how long all the last m runs, and you need to define that, and you're going to define as red something that went too far away from 3 times the variance. Everything, including noise, should get a little bit more, a little bit less, but if it gets way too far, that it breaks the normal distribution. This is not a normal distribution anymore, so you could consider that red. You also need one more thing. This is the coefficient of variance. You could have all your tests slowly getting worse, and a little bit worse, and a little bit worse, and a little bit worse. So if you track m runs, if you track all of them, you will see that the variance eventually breaks. But if you track the last 50 or the last 100, your average is growing. So you will not detect that it's getting worse because nothing ever grows outside of the accepted variance. So you need to take into account the coefficient of variance. There are tools that calculate this, and the coefficient of variance will tell you if the variance is changing. And Also, when you run a test, usually there is noise, so you run the exact same test n times, let's say 3, and pick the best result, because the average result is going to have a lot more noise. One example of how this works: I get all my tests, that takes this amount of time, so you graph them. You know, the points are my discrete tests. This line is the median, so that's my baseline. All my code should take around this time, what I'm testing. You get one standard deviation up and down, like 2/3 of the population is going to be in this range, but almost everything is going to be 3 standard deviations up and down. If anything gets out, CI should scream. And then I can verify it went down. No, it got faster. Do I know why it got faster? If it gets faster and you don't know why, you should check anyway. I mean, consider yourself lucky, but check, because it can get worse and then you will also not know why. So with this, now you need to know your tool. How am I doing with time? All right. I want to spark a little bit of competition, because I like it. There are 2 tools that you're going to need. One is the usual benchmarking. I already talked about Benchy. Your language will have the appropriate ones. There is plenty of shell scripts. But a bit more fancy is the load test. And eventually the stress test, or the when you need to keep it alive for a month and see if it dies. This is when things get complicated, and there is a bunch of tools that are open source. And in my opinion, the best one that I like the most was K6 by Grafana. Amazing job. One very important thing that I consider very useful is that what I want to test is an actual programming language. There is a lot of tools that the tool asks you, okay, you want to send the HTTP request to this server with this body, but what if I don't want to send an HTTP request? And I want to have a full programming language because I know what I'm testing. I'm going just to write. So that's something that I find very favorable, and not a lot of tools do it, so that's fantastic. Scales really well. So I tried this test. In my other server, I had a echo server, TCP, send and return the same packet, written in pure Rust using Tokyo. Like, I just want to make sure that it's like the simplest logic in the best performance. So I want to test the load testing tool, not the other server. And repeat, like, get a connection, repeat 100 times in a loop, generating a UUID, sending and waiting for the answer and verifying that the answer is the same. And then I wrote the same using my own tool called AMOC, a murder of crows. Murder of crows in English, group of animals. They have different names depending on the animal. When you have crows, the group of them is a murder because they are waiting for you to be dead to eat you. That's what my server does. It's waiting for your server to be dead to eat your server. So I wrote the same scenario in my server. This time is Erlang code. Start some like telemetry, this like for metrics. At the end, I'm going to just like print the statistics. The same, connect, generate the UUID, send it, wait for the answer, check that the answer is the same, repeat 100 times, disconnect. Except same scenario. The result was like this. I'm very proud of this because like AMOC is like the work for of a good friend of mine and me, and is on average 5 to 20 times faster to do the exact same load. So I met people working in Grafana somewhere, I don't know if they're in the public, but I met people through the corridors, not in the K6 team, but I told them, please, let's spark some competition. This was fun to do. And let's get a different scenario. This time in my other server, there is a Rust Tokyo best performance. I'm just checking static files, and I'm going to just read some static file and check that the answer is 200. And hey, where's my arrow? Move to the next. All right. Is it? Maybe I run out of battery. Okay, anyway. Same thing. This time I have written this test in Elixir because Elixir had a very nice, where is it? Here, and a very nice library to do the HTTP request. Elixir has lots of web tooling, so I wrote my scenario in Elixir. And again, this time I was 5 times faster to run the same thing. So I was very happy about this. I'm going to say one thing in favor of K6. I'm really jealous of the user experience. They did an amazing job. So again, I'm not ranting on K6. It's awesome. If you are a Go or JavaScript developer, you don't know what to do. It's fantastic, and it also integrates with Grafana. So, but when you're running load tests, you are like burning a lot of hardware. You need to generate a massive amount of noise. So if I want to test 20 million connections because it's Christmas or it's Black Friday in my e-commerce, and I want to test that it survives 20 million connections, then I'm gonna pay a massive difference in AWS credits running this test. So I just need to continue working on the configuration and user friendliness. But anyway, stop working. One more thing that you will need in your load test, and this is all the configuration was very user-friendly with K6, but this is one thing that I like in my tool. You will need things like throttles and coordinates. So one mechanism is a throttle that I can configure to change gradually from this amount of request to this amount of requests in per minute. This time I can change it to 2 different rates in steps. And my actors, so the connections, if you are familiar with Erlang, it's an actor model, so I can just spawn a virtually unlimited amount of them. That's the advantage. Another thing is that I may need to coordinate. For example, if I'm testing an e-commerce and everybody's going to buy something different, but a few people are going to buy the same thing, and I have 5 units, but 8 people want to buy that. So I will want to coordinate my actors to tell each other, okay, you 8, try it at the same time, and let's see randomly which one is the one that gets it. So I will need to create plans. So to pick like every 2 actors run a function, or every 5, or when you get all of them, and then actors as they are running, they are adding to this plan, and then later they will be told what to do. And one little last thing I need to finish because we're running out of time. Gathering data. Instrumentation is not metrics, almost, but it's not. So frustrating that I keep clicking here and it doesn't. Perf, for example, is just a front end to counters. Instrumentation is all the stuff the kernel and the CPU are doing. Perf is the one that gathers all that data and builds it into and transforms it into metrics. And this classic example of the kernel is what all your programming languages do with their performance counters, and then you use Prometheus, same idea. So in my tool, I do something very similar. When it matters, I scream, something happened, and then the backend that needs it picks up this data and transform it. This is one way. Every actor will run this function, but this is run inside of telemetry span. Telemetry span automatically measures the time my function took to run, and then it triggers this event when it starts, when it stops, and when it stops if it stops with a failure. And here I can gather the data. I know the timestamp at the beginning, how long it takes, and I can calculate all my metrics. So again, I expose this in my library, and with some basic gathering, but you can write your own. And one last quote. This is from the other creator of Erlang that I didn't have the chance to meet because he passed away. He said, when you write something, first make it work, second, make it beautiful, and then if you really have to, make it fast. And then it didn't fit in the slide, the continuation, because most of the times when you make it beautiful, it's already fast. But this, what I said at the beginning, you only care about code you have benchmarked, and benchmark is part of your offering, is part of the functionality, is the keynotes that the key points that I have for you. That is all from me, and I believe we have no time for questions, right? Or, oh, perfect, good. All right, questions. Thank you very much. Yes, that's a very good point. Now I need to drink. So I was telling you that to deal with noise, you do this like gathering statistics, the last n entries, and so on. But this only works when you have more than one run. So what do you do with the first run? I would say like, very often you already have existing code, so manually define some baseline and then let it build, let it heal. Define a baseline that is way too green, define something over optimistic, and then implement that mechanism. When you write code from new, and you get the chance to like write in your TDD cycle, think about how long it should take. What is the contract of your offering? Like you have a website that will deliver the static content in 5 seconds or within 100 milliseconds for a single operation. You're not even doing load. Yes. There is a little bit of manual decision at the beginning. Do that with the critical part of your code and let every other part of the code build its own statistics as you run. And that's how you define if the test is green or not. You need to define the scenario. The question is how do you define the threshold? At the beginning is manual. Right? Any more questions? All right. Oh, there is a hand over there. Yeah. Yeah, I will repeat the question. What kind of testing do I recommend in the CI/CD pipeline? I mentioned at the beginning the 3 standard ones is benchmark and load and stress. Benchmark and load, I believe, are the low-hanging fruits. Stress is a bit more complicated. And then the 1 month long, okay. In CI, for all the little libraries, we do have benchmarking. So for the XML parser, the JITs, these identifiers, base encoding, base 64, base 16, we do have benchmarks for all of that. I am still working on the self-generating statistics because I need to play with like saving things in cache on CI, so then it's fetched on the next one. That is a work in progress. I'm working mostly right now on that with Scrum, the XML parser, and distributed in-memory database that we have. That for performance tests, the usual benchmark, that is the easiest thing. We do it a lot. Far from perfect, it's work in progress, but I have an idea how to do it. There is a few ones that are already done the right way. For load tests, we do have load test in the big server in Mongoose IM. It was automatic at some point. Then Ansible changed versions and stuff started breaking, and we need to get back to that. But at the moment it's manual, unfortunately. Sorry? Yeah, yeah.
Thank you very much for a very interesting presentation.
Thank you.